You guys just have one more lecture with blank, then you're done. You do. Monday, it's like doing Q&A for whatever. Wednesday is not going to be there. That's the lecture you're doing your own. Technically, the Monday lecture you're doing your own as well. That's the cancer genetics one. Wednesday is he's not going to be there, or I don't know if he is or isn't, but he gives you like a MHC lecture, and you do it by yourself. And I'm not going to go do that one. I'm going to do the cancer one. The cancer one's way worse. And so I'm going to go over that with you guys probably the Sunday after Thanksgiving. So that's the Sunday right before your anatomy exam. So try to start planning ahead. Obviously, I know you guys have things. What do you guys have? Monday, Tuesday, Wednesday, then you're off? For USF, does anyone know what it does?
Wednesday's reading days.
Okay, Wednesday. So you only have Monday, Tuesday class?
Like one class each.
I don't know. I have no idea. Okay, so you've got a genetics Q&A, that's it, on Monday?
And then anatomy, there's no anatomy, right?
Oh, yeah.
Right.
Okay, yeah, so you don't have a lot to do next week, which is great. Obviously, Thanksgiving, so don't get stressed out the whole time studying, but don't do what I did and oh, well, I'll get to it, and then it's like Sunday, and then you have an anatomy exam on Thursday, right? The cancer one is a lot of shit, a lot of stuff. You guys have seen some of it. I posted the PowerPoint. That doesn't cover all of it, and it covers probably some things that Blank doesn't really care about, so keep in mind you should definitely read it. Don't just go off of my PowerPoint. But I'm going to do not this Sunday, next Sunday, then I'm going to go over the cancer one. I'm going to probably do it, I'm going to do 1 hour, one time, probably around 11 or so, and I'm going to go over all the cancer genetics one. Once again, I'm not going to cover the MHC one. That one, you guys have seen that like 4 or 5 times, guessing genetics, and hopefully you have some idea of it from Immuno. So therefore you should feel okay about that. And then after that, you have one more lecture with Blank on personalized medicine, which is like the coolest thing of genetics that we're going to talk about. Save it for the very, very end. But yeah, that's it. So you guys basically almost have all the info for this exam already, for genetics at least. So yeah, try to sort of stay on top of stuff going forward, because it's going to end and then you have a month off. And then we come back and then the actual work starts for second semester, right? This is where it kind of picks up a little bit. But yeah, so just sort of keep that in mind. So basically on this exam, I only have like 6 lectures or so. We got recombination, 2 GWAS, the cancer one, TCGA, and then, what is that? How many was that, 3? Yeah, and then you have the 3 other ones for the 2 self-study ones, and then the one on personalized medicine with genetics, and that's it. So a lot less information in terms of lectures. Moving forward, I posted a little mini PowerPoint thing for this. Does anyone have any questions on recombination? Does everyone feel good about it? What do we say when we mean there's like a predisposition for Huntington's disease? Does that mean you have to be born with the disease to get the disease? Is that the only way you can get Huntington's disease? You're either born with it or you're not? Let's start this way. Huntington's disease, all right? Do we see babies with Huntington's disease typically, or is this something that occurs later on in life? Later on in life. But we say that you can be predisposed to Huntington's disease. So how is it you can be predisposed to Huntington's disease from birth, but oftentimes we don't get the development until later on in life? Let's go back a little bit more. What causes Huntington's disease? It's repeats, right? What's the repeat? CAG. You have too many CAG repeats in the Huntington protein, or the Huntington gene for the Huntington protein, right? So we have too many of these CAG repeats. So when I say someone is predisposed to Huntington's disease, I'm saying that maybe, I don't know what the actual number is, let's say it's 30. If you have over 30 CAGs in a row in this part of this gene, you have Huntington's disease, all right? That's what you're going to have. If you have under 30, you're fine. Over 30, you're good. Oftentimes, people may be born, let's say if you're normal, you have only 2 or 3 CAG repeats in a row. Let's say that's the normal. I'm making up numbers here. Let's say that's the normal one, right? You have 2 or 3 CAG repeats. Over the course of your lifetime, will the CAG repeats increase or decrease possibly? Yes. Why would they increase or decrease throughout even me if I only have 2 or 3 repeats to begin with? That's due to unequal sister chromatid exchange, right? So sister chromatids also go through recombination. Does that do anything though? Is there any end result of having identical sister chromatids go through recombination? Am I changing genes between the 2 sister chromatids or changing alleles?
No.
what, by definition, what are sister chromatids? They're the exact same. So if I do crossing over with sister chromatids, do I change the genetic information in terms of the alleles or the SNPs? No, I shouldn't. However, sister chromatids still go through this recombination. We don't actually know why. I mean, I'm sure it's probably because it's the same mechanism, but there's no actual purpose to it. I don't get any exchange of genetic information because they are identical chromosomes. However, what can happen is if I go through that recombination event for sister chromatids, sometimes what happens? I get unequal sister chromatid exchange, which means that between maybe this one and this one, if these, let's say I have the 3 repeats right here, CAG. All right, let's try this again. You've got CAG and CAG on the other one. Normally, I want them to overlap just like this. I want the 2 chromatids, let's say I have these 2 right here, these are the exact same. My hands are the CAGs. The whole chromatid should line up like this, and then they go through that recombination event. However, because there are repeats, you actually can have issues where this may not be exactly overlap, and it can come down like this or like this. And that's sort of what's going on in this bottom picture right here, where we don't actually get the proper crossing over occurring. It's still occurring, but instead of it being a nice one-to-one overlap, it's off-center. Which means that what happens to some of this, what happens to initially blue and green, let's just call those the different sister chromatids. Blue had 3 CAGs and green had 3 CAGs. What happens now after I have this unequal crossing over? How many CAGs do I have at the top one? 2. Now I've got 4. So I went from having 3 to now having 4 CAGs. What did we say? What did I make up as the number we need to have for Huntington's disease? 30. We're still okay. However, what happens if someone, due to what they got from their parents, already has like 28 or 29 CAG repeats? They don't have Huntington's disease, but as soon as I get any bit of unequal crossing over, I can already get up to 30 CAGs. That's why they are predisposed to the Huntington's disease, because they were initially born with a high number of CAG repeats. Not enough to have Huntington's disease, but now that we have this unequal crossing over, we then can get to a very high number of those CAGs. Now we have the presentation of Huntington's disease. So keep in mind, identical sister chromatids go through recombination, which doesn't, once again, there's not like a point to that. There's not really any sort of advantage or evolutionary advantage to that occurring. It just does occur, and I'm assuming because it's the same mechanism as what happens with normal homologous recombination. Only the other big thing from this lecture is, what are the 2 ways we get increased genetic variability? I'm talking about making like gametes and going from parent to offspring. What are the 2 big ways that we have an increase? It's like half the slides out here are talking about it, right? What are the 2 ways we get what's up? Yeah, independent assortment. What does that mean? Independent assortment is talking about what? Mitosis or meiosis? Meiosis, right? It's basically how, when we have everything lining up in that metaphase plate, it's going to be random. As in, maybe for chromosome, the first set, you've got maternal on one side, paternal on the other, but then the other side is flipped for the one below it like that. So you have independent assortment, where things are lining up independently of each other. And the second one is recombination, right? You have this initial, we have 2 basically, I've got genetic info from mom, genetic info from dad, but when we make gametes, what are they doing? They're getting recombination between their maternal and their paternal, and therefore you're getting new variations or new combinations of alleles and different SNPs that we may not have seen before in any of the population. So it's another way to increase our variability. Make sure you know the differences between meiosis and mitosis, right? How many divisions do we have for meiosis? 2. What separates during meiosis 1? Is it homologous chromosomes, or is it the actual individual sister chromatids? Homologous chromosomes are the homolog, whatever blank likes. The homologs separate during meiosis 1. So what that means is during meiosis 1, I've got chromosome 1 and chromosome 1 doubled on the metaphase plate. They line up together. So when I draw that, what we have is you're going to have chromosome 1. So let's say this is, yeah, the screen isn't working. So let's say this is me. I'm making my gametes during excuse me, meiosis 1. I'm going to have the maternal that I got from my mom and my paternal I got from my dad lining up right next to each other on the metaphase plate. Chromosome 1, chromosome 1. One maternal, one paternal. So as you go all the way down that metaphase plate, you're going to have 23 pairs, right, going all the way down. And then those separate during meiosis 1. During meiosis 2, what are we separating? Sister chromatids. We are basically breaking and then breaking again. Keep in mind, both mitosis and meiosis, I must go through S phase first. I must duplicate all of the DNA. If you don't have duplicated DNA, I can't do mitosis or meiosis. Those are a lot of the big things. And obviously here, another way we can talk about sort of changes occurring can be through strand slippage, right? Where you can have something occurring where what normally happens, we talked about this when a DNA polymerase adds a tautomer. What would we talk about for the exam 1? What happens once I immediately start adding and I pop off like this? What normally do we do? How do we get rid of this? Yeah, the DNA polymerase has an exonuclease, right? An exonuclease identifies that and works back Pac-Man, chops it off, and then adds it back again. That's what happens a lot of the time. But what can also happen with that same issue is something like this, where this is going to pop off, but even though it pops off, because I'm in an area where a bunch of shit is repeated, it's really easy to continuously add things, and that loop then comes back in. And then eventually what's going to happen is, once I get all the way through, I can actually have this broken open, like not broken open, but pulled open, and now I have more repeats in there than I had to begin with. Another way we can get an increased number of repeats, in this case they use C8, but it could be even like CAG could work, things like that could also work. So just be aware of that moving forward. Yeah, that's a lot of the main big things from there, so not anything too crazy. I feel like it kind of doesn't really get that complicated until the GWAS lectures. That's what we'll focus on now. Last thing, when does recombination occur? What phase exactly? I believe it is prophase 1. That is what Blank mentioned. My year we had some, I think at one point said metaphase, and then he also said prophase. Remember what he said in lecture? He said prophase? Or no? Yeah, okay, cool. So prophase 1 is when recombination is going to occur. Anyways, yeah, that's the first lecture. A lot of it should hopefully be things that you guys at least are pretty comfortable with. So now we're looking at genome-wide association studies. It combines everything you guys hate. It's all the technology shit, plus now using that and looking at the entire genome, looking at SNPs, and basically the idea of this is the end goal is we're looking at diseased alleles. We're looking at alleles that are not always, but for most of the examples in this lecture, we're going to be looking at someone has a disease. I want to figure out what gene causes that disease. It's kind of easy for us now, since we have all this information, that we already know, well, I know if it's Huntington's disease, I know it's the Huntington gene. However, in the beginning, when we didn't have any of that information, we had to work all the way from the beginning to figure out where that gene is. So you can't go in, you could technically go in and sequence every gene in that person, plus every other person that has Huntington's disease, and then look at variations between them. That would take a very, very long time to do that for everything, for every gene in particular. So instead, we're looking at markers near where those genes are, and that's easier for us to work with. And that's what the whole idea of this lecture is going to be. So the biggest word from this whole lecture is haplotype, right? Or haplotype block. When this thing. Can anyone tell me what a haplotype block is? Just like in general? What is it? If I tell you there's a haplotype block, what's up?
It's a block of DNA that typically stays together without being recombined.
Exactly.
Hotspots on either side.
Exactly. So all it says, when I say you have a haplotype block, is a stretch of the DNA where everything in there will always run together. What I mean by that run together is, even when I'm talking about during meiosis, when I'm making gametes, so from generation to generation, you're always going to see that block, which means that within there, that DNA is always going to be the same. So if I have a gene in there that has big A, allele big A will always be in this block. What else will be with it are going to be other things that are unique to that DNA. What are some other examples that we talked about of things, excuse me, getting over a cold, are things that are polymorphic to different people, however, they don't cause changes in phenotypes. What are other examples of things we've seen? So what are things that are different between me and you, but they're not different in terms of different genes? That's what I'm asking.
VNTR.
SNPs, VNTRs, exactly. And these are things that you need to just be really, VNTRs we're going to talk about a little bit, but you're expected to know what we've already talked about from exam 2 on VNTRs. Those variable number tandem repeats, right? Where the numbers are repeated, it's the same sequence repeated, but different number of times in different individuals. So VNTRs and SNPs within this block are always going to be the same if they're one haplotype block. So this block in particular, I'm going to tell you right now, let's just say it's got the big allele A, and I know if you have this haplotype, this SNP right here is going to always be a G. This SNP right here will always be a T, and maybe there'll be a VNTR right in, okay, this thing isn't working, but there'll be a VNTR right there as well that'll always be repeated 5 times. And in that block, it's always going to be that. Unless, now I'm talking in absolutes here, the problem is, even with this, we can still have recombination within here. We'll get there and eventually, but for now, for the simplistic view, a haplotype block is an area, a block of DNA where no recombination ever occurs within there. That's not exactly true, because it still can, but let's say very low chance of recombination occurring within this block. Therefore, this block is going to always travel together. When I'm saying travel together, I'm talking about going from me to my sperm into my son or daughter. Right? So the block always travels together from generation to generation. Here's the next thing. When we talk about haplotype blocks, we're talking about on a generation or a population level sort of definition. So you don't just have 2 haplotype blocks. Maybe that is, let's assume like normal Mendelian genetics, right? You have big A and little a. Let's say whatever this gene is, you've got big A and little a, doesn't matter which one causes what. There aren't just 2 haplotype blocks for this gene, for like the DNA there. There's a shit ton of haplotype blocks. However, if your dad or your mother has 1 haplotype block, when they make their gametes, that gamete will also have that same haplotype block. So there may be a number, maybe 100 in the entire population. There may be 100 total haplotype blocks that have big A within it. However, maybe 1 haplotype block, the other SNPs are GGGGG, and they have the big A for the big allele A. A different haplotype block can be T and big A. Does this make sense? It's not just big A, little a, only 2 haplotype blocks in a population. There is a whole bunch of haplotype blocks for whatever block we're talking about, and each block is unique in terms of the total number of the unique SNPs they have, the VNTRs, and whatever alleles for the genes they have. But it's not just like a one-to-one thing. And this will make more sense as we go through it. But really, it's really important to understand this to really get a good idea of what's going on all the way through. So when we talk about haplotype blocks, and we're going to look at percentages later on, we're saying in a population, maybe 1 block is more prevalent than another one, or vice versa. But that doesn't mean that those are the only blocks that we see in the entire population. So think of this as on a population scale. Everything in this lecture is about that. It's genome-wide. It's every human's genome. We're looking at all of the different blocks that we're going to have. So when we talk about changes to haplotype blocks, which does happen, we're talking on a very big time scale. Not just like me happening within me, but over generations, I can then get a new haplotype block forming. So this whole thing is still very fluid. Keep that in mind. Fluidity is really, really important as we move through. Also in this lecture, and the next one, Blank did a lot of research in this. All of these have Blank as the main author. So make sure you know these very well. Right? All things we need to know. He says look at the box. Are these figures in the lecture or no? Does anyone know? find out because he mentions he wants you to look at those. Once again, he said they may actually be in the presentation, so we'll just keep an eye out for